In this short video, I would like to share with you what I've learned by completing problem scenario 2A. This bioremediation problem scenario focuses on the design and creation of a microbial fuel cell. It actually epitomizes biotechnology. This design solution uses living organisms, bacteria, to make a product, electricity. The actual challenge asks us to use bacteria to be able to have them metabolize organic material and in the process give off electricity. They are enough to generate enough current to power a small light bulb or motor, and the design is to be scalable to be able to process greater quantities of organic materials such as human-generated waste found in wastewater treatment facilities. The biology within this biotechnology design challenge focuses in on exoelectrogen bacteria. These bacteria, as stated, can actually break down organic material. They metabolize the organic material and in the process give off electricity through electrons. They are geobacteria. The technology focuses in on a fuel cell. In the fuel cell, it has the components of any fuel cell, an anode chamber, cathode chamber, electrodes within both, and also then a completed circuit to be able to use the electricity that is generated. Ultimately, my initial brainstorming was very light. I didn't know much about the bacteria, nor much about the whole idea of a fuel cell. It sounded as though the bacteria might be used in compost, so I knew I needed dirt and debris for those microbes, and I needed a completed circuit in order to be able to light my light bulb. After doing some research, especially finding some designs from students, I was able to have a better idea of what this system would look like. Standing on the shoulders of giants, in this case students, I could see how they were creating their fuel cells and separate anode and cathode chambers. Research also showed how you could have anode and cathode chambers in one particular container, but I wanted to work with the two separate chambers. So my original design was actually a student design. The upper left-hand corner is a design by Gene Snyder, a high school student. I thought it was a very simple design, and it seemed to be one that I could actually construct without a lot of difficulty. After a conversation in class, however, and Dr. Wells giving us very detailed step-by-step directions, it sounded as though it might be better for me to use the Wells microbial fuel cell in order to be able to be successful. I ordered the plastic containers for the anode and cathode chambers. I sent those ahead to Fairbanks where I would be constructing this particular fuel cell. All the other materials I thought I could find easily there. Once I got to Fairbanks, I ended up going back to my original thought because the plastic containers never got to Fairbanks. So Home Depot had the PVC pipes and those pieces that were necessary. You'll see my final design is a combination of the student design, and I used Dr. Wells' step-by-step directions in the construction of this to make sure that I had the right quantities of all parts. It's actually a very simple design. On the left-hand side, you'll see the anode chamber. It is an anaerobic chamber. I was able to, it's very easy using the PVC pipe. It fits together tightly. The cement then holds it in place. The anaerobic anode chamber, I used duct tape to make sure that it was going to be anaerobic, and also around the actual electrode that was coming out of the top, there was a cap that I drilled a hole in the top of the cap in order to have the electrode coming out of the top. On the right-hand side, you'll see the cathode chamber. In the next construction, I would give it a lid as well because the bubbling of the aquarium pipe, or the aquarium pump bubbling the water actually spilt some water out in the process. I would then have a cap on that one as well where the aquarium tubing would be able to go in as well as the electrode tubing. Both sides were connected with alligator clips to the multimeter voltage meter. The calculations needed to be done to determine the proton exchange membrane, or the salt bridge. That particular tube I needed to cut. Ultimately, it was 3.45 inches. The calculations for that was simply using the volume of a cylinder. I only had enough agar to create 100 milliliters of the agar, and the salt water, 100 milliliters is the same as 6.10 cubic inches. Using the volume of a cylinder and working backwards, I was able to determine that the height of that tube needed to be 3.45 inches, and that was what I used to cut the tube. The electrode construction wasn't difficult, but it was difficult finding the electrically conductive adhesive. Ultimately, an auto parts store had rear window defogger adhesive, and that worked well. My next challenge was finding benthic mud. I was on a trip that took me from Virginia to Texas, from Texas to Denver, and ultimately ending up in Fairbanks where I would be constructing the microbial fuel cell. I stopped in Denver and actually collected some benthic mud at the Cherry Creek Reservoir, but was unable to use it within the 24 hours to create my fuel cell. So in the end, I was able to find benthic mud at the base of the Chena River. The Chena River had some open water, and it flows through the center of Fairbanks. My data shows that I started with 0.001 volts, and I ultimately took more readings days 1 through 8 because I was able to do multiple readings, became a little addicted to finding out what my voltage was. Days 1 through 4, there was an increase in my voltage. It plateaued between days 4 and 5 to around 0.360 volts, spiked on day 9 at 0.395 when some water was added, and that might give us a clue of some way of increasing that particular data. It's much easier to see this trend in a graph, so you can see once again that it from days 1 through 4 was this pretty steady increase in voltage, plateaued from days 4 through 8, and spiked a little bit at day 9. In the end, I did not have enough current to light the light bulb, but my voltage did at least maintain around the 0.385, 0.395 toward the end. Some improvements. I think if I increase the size of the different components, I might be able to have more voltage, increase the volume of the anode and cathode chambers, increase the salt bridge, the size of the carbon cloth. If I increase the numbers, more electrodes, and have multiple MFCs in a series and parallel circuit, I think there'd be an improvement. And other modifications, a cap on the cathode, and maybe different mud. This is what that new design might look like. Instead of 3-inch diameter anode and cathode PVC pipes, I would use 6-inch. Instead of having it taper to a 3-inch salt bridge, I would have it taper to a 3-inch piece. I'd have 2 electrodes, 8 centimeters by 8 centimeter carbon cloth in both anode and cathode chambers, still connected to a multimeter. It was easy to be able to take the readings with that. That would be one microbial fuel cell. I would put 3 of those together in a series, and with my 0.385 as my average one single MFC, if I put them in a series, if I had 3 of them, I would triple the volts. And I think that would be enough for us to be able to light the light bulb. And then if I had the series modules and then put them together in a parallel circuit, I would be able to increase my current. So 3 individual microbial fuel cells in a series to increase my volts, and then 3 of those then to increase my, to create a parallel circuit to increase the current. There are designs out there that are scaling this up for real-world use. Bruce Logan's work at Penn State has some large areas where he is doing some reverse electrodialysis along with the creation of the microbial fuel cells. In place of salt water in the cathode chamber, he's using ammonium bicarbonate. He's having success at 0.9 kilowatts per hour of electricity per kilogram of organic waste. If we can be successful in generating this kind of power, it's a renewable resource. It also is then going to actually break down a waste material, and one of the final results is clean water as we are in the cathode chamber able to generate that water. So thank you for listening. I'm excited to see what everybody else has been able to complete and what their microbial fuel cells will look like too.